Alright, this video is about how to prepare and run a TLC. In order to get ready to run a TLC, the first thing you need to do is have a chamber, and in this course we're going to use these small sample vials as chambers. Our TLC plates fit in them very nicely, and in order to prepare the chamber, what you want to do is you want to put in 2 pieces of filter paper. The 2 pieces of filter paper have 2 purposes. One is to keep the TLC plate from sliding on the bottom, and 2, it allows the solvent to move up the wall of the container so that the atmosphere inside the container gets saturated with the solvent that you're using very quickly. The shape of the 2 pieces of filter paper isn't very critical. You want one piece of filter paper that fits neatly into the bottom of the chamber. So there, and then another piece of filter paper that sits up along the wall. It's best if the piece of filter paper that sits up along the wall is curved and long enough that it holds itself in place so it doesn't fall down while you're trying to work with it. So I'm going to cut one that's just a little bit bigger. And there we go. So we have 2 pieces of filter paper in there, one on the bottom and one on the wall. And now our TLC chamber is ready. Alright, so the next thing we're going to do is cut a TLC plate. Now in this class we're using aluminum back TLC plates. This may be the most dangerous thing that you do in the organic chemistry lab. So pay attention to this procedure. In order to cut an aluminum back TLC plate properly, what you do is you take a 4 centimeter wide strip of the TLC material, and the white side is the side that has the silica gel on it. The sort of silvery side, that's the aluminum backing. When you cut TLC plates, aluminum TLC plates, you always want the silica gel portion down. The width of the TLC plate you're going to use depends on how many spots you're going to try to put on that TLC plate. So for example, if I were just running a TLC with 3 lanes, a centimeter or just a little bit more is good. In order to cut a TLC plate, you put a steel cork back ruler down on the TLC plate, and you need to remember to keep that firmly held so that the aluminum TLC plate doesn't move while you're cutting the TLC plate. Then you take a razor blade and you hold it like a pencil. Okay, you hold it like a pencil, and what you're going to do is you're going to drag the tip lightly along the surface to put a score in the aluminum. And you don't want to try to cut it through in one pass. You want to cut it through in a couple, maybe 2 or 3 passes will usually do. Once cut, you pick up the TLC plate, and you want to make sure that the edges are quite smooth. And so you can see oftentimes when you've just cut one that there's some jagged edges, and so usually what you do is you simply touch up the edges with the razor blade, and that will help the TLC plate run in an even way. So that's cutting a TLC plate. Now that we have our chamber and we have our TLC plate, the next thing that we need to do is get our sample ready. Okay, so I'm going to scoot this off to the side. In order to run a TLC, you need just a few hundred micrograms of compound total, and you're only going to load a small fraction of that amount. And so one good way to prepare samples for TLC is to get a test tube rack and 2 small test tubes, say if you have 2 samples that you want to run. So in this example I'm going to use 2 different compounds that I've just pulled off the shelf, but this could be a reaction mixture and a starting material. If you have 2 starting materials, you could run a TLC plate with more compounds. So what I'm going to do here are my 2 sample compounds, and I'm going to grab a TLC, or I'm going to grab just a Pasteur pipette. Now to give you a sense of how little material is required, I don't know if you can see this, but I've opened this chemical, and I'm just going to dip the end in. Notice there's no pipette bulb on there, and I'm going to push out all but just the last little drop. So again, I'm going to push out with my fingers all but the last little drop. So that little residue there, that's enough to run a TLC. So I'm just going to stick that pipette in there, and I'm going to grab a sample of my other compound. You can use a long pipette because it's a big bottle and it's almost empty. So again, I'm going to push out all but the last little drop of compound in there. And if we spotted those neat compounds that are undiluted, directly onto the TLC plate, what you would see is the TLC plate, or the spots on the TLC plate, would be very streaked. They would be far too concentrated. You will have loaded far too much compound onto that TLC plate. So what you always need to do is dilute them. The amount you dilute them is more of an art than a science, because different compounds stain differently and run differently on a TLC plate. But you saw I just took 2 small samples, and I'm just going to dissolve in any organic solvent. I'm going to dissolve those and dilute them in like a mil or a half a mil of solvent. Doesn't matter what volume exactly. And after your first TLC, you'll know whether you need to concentrate the samples more or dilute them more. Acetone is a great solvent for making these TLC solutions. So you see I just put the solvent right into the Pasteur pipettes to rinse them. And so now what I have is I have 2 samples of compound that are diluted in some solvent. And again, the solvent choice doesn't matter. So that's sample prep. I've completed my sample prep. I have my chamber, I have my TLC plate, and I have my 2 different samples. Now, there are a couple of different configurations for spotting TLC plates. And there's one extremely good one for monitoring reactions, so that's the one I'm going to show right now. So let's imagine that this is your TLC plate. If you're monitoring a reaction and say you have 1 starting material, what you want to do is you want to put 3 spots down. On this spot, you're going to spot just the starting material solution. On this spot, you're going to spot just the reaction mixture. And on this spot, you're going to spot the starting material and the reaction mixture together. The idea is that if your starting material runs up this high on the TLC plate, say after we've run the solvent to there, we should see that starting material here. And if in the reaction you form some product, you'll be able to see that product at a different position. You'll also be able to see whether there's still some starting material remaining. So this would be maybe an incomplete reaction. Alright, so this format gives you a lot of information about a reaction that has 1 starting material. If you have 2 starting materials, perhaps a 5-lane TLC plate's a better idea. So let's look at how you might do that. In this case, you might be interested in monitoring both starting materials. So now you would want 5. On this side, you would have starting material 1. On this side, you would have starting material 2. In the middle, you would have only the reaction. And then on these spots, you would cross. So this would be the reaction mixture spotted with starting material 1. And on this spot, you would have the reaction mixture spotted with starting material 2. So let's say starting material 1 runs at that position. Starting material 2 runs at that position. And let's say our product is right here in the middle. What we would observe in all the cross spots is we would see the product, and perhaps we still see a little bit of starting material 1. So this is just the reaction mixture. So this tells you, this lane right here tells you what's going on in the reaction mixture. It looks like starting material 2 is consumed. Starting material 1, there's just a little bit left, but there's certainly product that has been formed. Okay, so in this example, I'm going to use I'm going to pretend like one of these 2 test tubes contains my reaction mixture, and one of these 2 test tubes contains my starting material, and I'm just going to do a 3-lane TLC. So I'm going to design the TLC plate like this, where I have 3 spots. So in order to put those spots, those origins for the TLC, we're going to need to make 3 pencil marks. Okay, so I have a pencil here, and what you want is a fairly soft leaded pencil. I have a number 2 pencil here, which isn't super soft, but it's fine. And you don't want a super sharp tip on that. And the actual location of the spots is not so important as long as you have them roughly in a line. And you want them off the bottom of the TLC plate a little bit, because we're going to set this in some solvent, and we don't want the compounds that we put onto these spots to be in the solvent. So I'm just going to put 3 spots, light pencil marks, onto the bottom of that TLC plate, and I'll hold it up closer so perhaps you can see those 3 light spots. Now what we need to do is we need to deliver these 2 samples onto that TLC plate. In order to do that, we're going to use a very fine glass tube, TLC capillary tube. Oftentimes when you pick up a TLC capillary tube, and we'll learn in this course how to make those TLC capillary tubes, the end of the capillary tube isn't suitable for spotting a TLC plate. So let me give you a sense of this. So if we zoomed in and had a look at a capillary tube, this is the end of the capillary tube. If we dip that capillary tube into some solvent, the solvent's going to flow up here, and there's going to be a little column of solvent there. But if the end of the capillary tube is jagged and broken at an angle, when we put it down on the TLC plate, first of all, the compound isn't going to drain out onto the TLC plate and make a spot, and secondly, you're going to see that it's going to dig in and damage the TLC plate. What we want is we want the end of the capillary to be nice and square, nice and squared off. So this would be the end of the capillary tube. So now when you press it down on the TLC plate, the solvent flows out, you don't damage the silica gel surface. So in order to take a capillary tube, even a very fine one, and take it from having a jagged end to a very square end, we need to square the end off. All right? This is going to be a little bit difficult to see in the video, but I'll do my best. In order to do that, what you do is you take the TLC capillary tube and you put it on your hand, and you rest the very end of the capillary tube on your finger, and you take a piece of emery cloth that has a very hard grit on it that will score glass, and you simply take one little rub across that capillary tube, and then the end will just break off. So about a ½ centimeter of that broke off, and if you could see it, you would see that now the end of this capillary tube is nice and squared off. So that is the way you square off a capillary tube. Oftentimes you'll want to do that also if the capillary tube gets clogged or it has a difficulty running. So now what I'm going to do is I'm going to spot my compounds, and again I'm going to take one compound and put it on the left, one compound and put it on the right, and then both compounds will be spotted in the middle. So I'll start at the left. Usually in my typical pattern I would do the starting material on the left, and what I'm doing now is I'm just tapping the TLC plate and then letting the solvent evaporate. So I tap and let it evaporate. The idea is you want to keep the spot small. So I've now spotted, took me about 4 little taps to empty out the capillary tube, and put that same material on the middle spot. I was just doing little itty bitty taps here. Okay, and so now I've got that compound there, and if you could see, which I know it's difficult to see, there's just a little bit of silica that's come on to the end, so I'm just tapping out the TLC tube. If I break it, no problem, I just square it off again. So now this TLC spotter has a little bit of that first compound in there, so what I'm going to do is I'm just going to simply rinse it out. Rinse it out by dipping it into some solvent and then just blotting it out on a paper towel or a piece of paper. And so that will essentially remove all of traces of that first compound out of the tube. Once the tube is cleaned out, we'll spot compound 2. And I'm going to spot it on the right one and the middle one. And each time I'm tapping and then letting the solvent evaporate off the TLC plate. Okay, so now I've got a little bit of silica gel that jammed up the end of the tube. So I'm going to take off the end, just took off a little, like 1/3 centimeter of that tube. And now I'm going to spot again. And I'm spotting the right 2 spots. Okay, so now we've completed this, and we can set our capillary tube somewhere where we can find it again, which isn't always trivial, and we can put the emery cloth back in the beaker that has the emery cloth available for the class. Now if we just look at this TLC plate, it just looks like a plate that has 3 spots on it. We can't visualize the compounds. In some cases we can confirm that we've spotted something on the TLC plate using a UV lamp, just to make sure we actually transferred the compounds. Usually we don't do that step, but let's give it a try, just since this is kind of an instructive video. So I'm not sure if either of these compounds show up by UV. We'll just have a quick look. There's not a guarantee that a compound will show up, so this is not a, if you get a negative result here, it doesn't necessarily mean there's nothing on there. So I'm going to try to turn on this. Ooh, I hope you can see that. One of those compounds is UV active, and so you can see 2 bright pink spots where we spotted that compound. In the absence of the UV light, it looks like it's just a plain TLC plate. Okay, so we know we've spotted material onto that TLC plate, and now it's time to actually run it up. So in order to prepare our TLC chamber, what we want to do is we want to put a little bit of solvent in the bottom of this TLC chamber, and we want the solvent to soak up this soak up the wall of this TLC chamber on this piece of filter, this larger piece of filter paper. In the bottom, we don't want the solvent to be anywhere near those pencil spots. So usually I try to wet the filter paper and then put like a 1/2 millimeter more of solvent in the bottom. This is most easily done with a pipette. If you're really good, you can pour it. So what I'm going to do is I'm going to open up my TLC chamber, and I have some solvent here, and depending on the compounds, you'll need a different solvent polarity. This one happens to be 25% ethyl acetate and hexanes. And so what I'm going to do is I'm simply wetting the TLC, or the filter paper that's on the wall of the TLC chamber, and pushing it along the wall so it sort of behaves and stays on the side. We don't want it to get in the way. And then I'm adding enough so that I see just a thin layer of solvent over the top of the bottom piece of filter paper. That way I'm assured that the whole bottom of the TLC plate is going to touch the solvent, but that the solvent layer is not going to be above the dots or even close to touching them. You don't want the compound to dissolve out into the TLC solvent. So it's best practice if now you cover the TLC chamber for a moment and let the atmosphere inside the TLC chamber become saturated with the running solvent. That will keep the solvent from evaporating off of the TLC plate when it's in the chamber, and it will allow more reproducible TLCs. So that was probably long enough. And so now I'm going to use tweezers to gently put the bottom edge of the TLC plate on the bottom and then lean it up against the wall and then replace the top. And it's very important that you replace the top because, again, you don't want it evaporating off. So I've put the TLC plate in there. I don't like it leaning quite that much. I'm going to lean it just up against the wall a little bit. And then I'm going to put this cap on, and we're going to wait. And you can wait a variable amount of time. What we're using here are 4-centimeter TLC plates. TLC technology has come a very long way, and typically a 4-centimeter TLC plate is more than enough to resolve even compounds that have very similar polarities. And there are tricks to get even better resolution on such a small plate. We used to use much longer TLC plates, but I think it's very reliable. In fact, in my research, I only use the 4-centimeter TLC plates. It saves a lot of material and a lot of time because you don't have to wait for it to run up quite so far. So the idea here is that we don't want the solvent front to reach the top of the TLC plate. So if you were observing what's going on, the solvent front is slowly moving up the TLC plate, and although we can't see the compounds, they're being carried along at different rates. What we want to do is, before the solvent front reaches the top of the TLC plate, we want to pull it out and we want to draw a pencil line across the TLC plate. That will allow us to calculate an RF. An RF is the fraction of the distance that any given spot traveled. So this distance, we define that as 1. This distance is some smaller amount. Let's say it's 0.25. That would be an RF of 0.25, 1 to 0.25. And you can just calculate the ratio of those two. This one looks like it has an RF of like 0.45 or something like that, the way I have it drawn. Okay, so an RF is the retention factor, or the percentage of the complete distance the solvent traveled that was traveled by any spot. So before it runs off the top, I'm going to pull this TLC plate out. I'll show it to you. So you can see very briefly where the solvent ran to, and I'm going to mark that with a line so I can calculate RFs. So now, if everything worked well, I should be able to see that the compounds have moved some amount. And of course, for an ideal separation or visualization, you want the compounds to move some amount off of the baseline, but not all the way to the top. We know one of those compounds at least is UV active, so it's always a good idea to start by checking your TLC plate with the UV lamp. So I'm going to do that. I'm going to turn the UV lamp on and I'll try to show you. So you can see that one of those two compounds moved, oh, it looks like an RF of about 0.75. If you look very closely, you can see that that material isn't entirely pure. You see a smaller spot with an RF of about 0.45 in that lane. The other compound I've spotted is not UV active, and so if we wanted to visualize that, we're going to need to use a staining protocol, and that's what's next. Okay, so in order to stain a TLC plate, you need some sort of chemical stain. Typically these are acid stains because the way we're going to visualize the organic materials is we're going to literally oxidize them or burn them up using a combination of acid and heat. One particularly good stain that's very general for many functional groups is called phosphomolybdic acid. This is a 10% solution of phosphomolybdic acid, weight by volume, in ethanol, a particularly good TLC stain. So I've got my stain, I have my TLC plate, and now I need a heat source. There are two common ways of burning TLC plates. One common way is to use an air gun, an air heat gun, so it looks like an industrial strength hair dryer. Another way is to use a warm hot plate, and that's the way I'm going to do it in this lab today. So in order to stain a TLC plate, the first thing you need is your TLC plate, some tweezers, the stain, and a heat source. So I've not adjusted this hot plate. Hopefully it's hot enough to allow us to do this visualization. This hot plate will be set up in the hood so that you can use it at any time. So the first thing you do is you dip the TLC plate into the stain, and you don't want to dip it much below or much above the solvent front line that you drew on the TLC plate. So you dip it just enough to cover the places where the compounds might be. So, and then you dab off the extra phosphomolybdic acid and ethanol solution until the TLC plate is fairly dry. And then what you're going to do is you're going to heat it up, and you'll heat up that TLC plate for variable amounts of time, and you'll observe first the solvent evaporates off. That's what's happening now. And then the compounds that are on the TLC plate will be oxidized, and then you will see them appear on the TLC plate. So if you'll recall, when we used UV activity, we saw the two compounds on the right, one there and one there. So those compounds were actually in lower concentration than the compounds on the left. The compounds that we couldn't see, the other material I used is right here. It has an RF that is slightly higher. It traveled further in the same polarity. Neither of these compounds is entirely pure. I see other spots other than this dominant spot. I see a second spot here and a faint spot there. So there are multiple things in that material. And remember, when we were visualizing by UV activity, we saw a spot here and then we saw a spot below it. Oftentimes, if I'm working with compounds that have UV activity that show up under the UV lamp, I will take a pencil and circle them under the UV light and then stain them. In order to visualize compounds with UV light, though, you have to do them before they're oxidized. Once they're oxidized, they're all burnt up. In any of the chromophores that might have been interacting with the light will be burnt, and you won't see anything under UV light. The plate will appear blank. So that's a summary of how you would prepare a TLC plate and run a TLC. Before I wrap up, I wanted to take an opportunity to show you the TLC plate up close. I know I was working down here on the bench, so I'm going to try to hold it up to the camera and then describe what you can observe. So this is, relative to my position, this is the left lane, this is the middle lane, and that's the right lane. And you can see that UV active spot was in the right lane, and those spots did burn. There's a spot there and a spot there where it was UV active. The minor compound, which was down here when we visualized by the UV activity, was too dilute to burn and be visualized. You'll often find that UV activity is an extremely sensitive way to visualize the TLC plate. So compounds that are UV active show up even when you can't see them by a chemical method. In the left lane, you can see that there's a lot of this material that I spotted on the left, but there's also an impurity here and another impurity there that's only visualized when we oxidize. So these compounds don't have a chromophore, and that's what the TLC plate looks like. If we wanted to calculate RFs, we would measure this distance between the origin spots on the top and then calculate the distance that the spots traveled relative to that total distance. It's a percentage of the total distance that the solvent traveled.